Okay, I'm going to move quickly through the previous ones. We already have considered this, so I'm just going to where did we stop? And we have seen the actual turbine, the actual boiler, and thanks for those. I got 4 students who made some animations on the WhatsApp, and this was excellent. So I hope every one of you should have opened this and have seen that what is the actual plant we are looking for. Okay, so as we engineers here, we have we have to work as I mean to understand the field, and this is what I have already given, and 4 students already submitted that. And first, thanks for them, and I hope everyone will be able to look at this and. Yeah, and you can listen to this while you are eating, playing, or whatever. I think it was useful. Thanks for those turns. Okay, today we are going to consider, as we mentioned, the simple cycle, which is uh, the actual plant, but simplified. Simplified means I'm going to consider only the 4 units here: a boiler, turbine, condenser, and pump. So this is the simple cycle, and this is called the rankine cycle. Rankine is the scientist who made that. So it has a turbine, it has a condenser, it has a pump, and boiler. So these are the 4 elements. We are going to make the cycle for that. We're going to make the analysis for this one, and then later on we can modify to reach the real plant. Another assumption here is that we are going to consider the ideal cycle. Ideal means that all processes are reversible. For example, the turbine it will be isentropic. For the pump it will be isentropic. There is no pressure losses here. Regarding the pressure losses, I wanted to indicate this because I got some confusion there. When I go from 3 to 4, then definitely there is an increase in the pressure because there's a pump here. When we go from 1 to 2, definitely there is a reduction in the pressure. But when I go from 4 to 1, yes, there is a pressure loss. Remember, look at this at a electric circuit. When you have a voltage from 4 to 1, the current will go from 4 to 1 if the voltage at 4 is higher than the voltage 1. So definitely the pressure at 4 has to be higher than 1 for the flow to go. Without difference in pressure, the flow will not go. But what is the difference here? If this is 10 megapascal, this will be 9.9 some 9 megapascal. So we have small losses here, and therefore we can neglect that. So in the ideal cycle, we would say that the pressure 4 is the same as 1, the pressure 2 is the same as 3, but then there's an increase the pressure here and there. So ideal cycle means we neglect the pressure losses in those, and then we consider isentropic expansion in the turbine and compression in the pump. Okay. Then we'll go to the next one here. We will have 4 processes, and as you see here, we have 4 processes. Process 1 to 2, which is in the turbine here. So I just got the figure here so you can see that. So from 1 to 2, there's an expansion in the turbine, and of course we get work. So this is the one of the process. The second process is from 2 to 3. The 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 steam out of the turbine at 2 goes to condenser, and then it is condensed to be liquid water here. So process 2 to 3, vapor condenses to liquid, and of course there's a heat transfer to outside, and this is done by cooling water. We pass cooling water, and this will cool the steam and gets liquid here. Then from 3 to 4, we have liquid is pumped into the boiler. So this pump will pump the water, mean increase the pressure, normally from 10 kilopascal to around 10 megapascal. Then this will go here into the boiler, which is 4 to 1, where it is heated, superheated, then go to the turbine and so on. So this is a cycle here with this 4 process. Please stop me at any time if you have any questions. Okay. So this is the engineering model here. This is the 4 elements. And of course, we neglect here the kinetic energy. Kinetic energy is neglected in all of them. And potential energy is also neglected because these are small in the case of boiler, turbine, condenser, and pump. Of course, there is kinetic energy change, there is a potential energy change, but these changes will be small with respect to the change of enthalpy. And of course, here we assume that the pressure losses are neglected, and also we consider that the turbine and pump are adiabatic and reversible, so it is isentropic. All right. Now we study the analysis for each one of them. For the turbine here, the turbine, of course, there's an equation here. There's plus kinetic energy plus potential energy. Those all neglected. So these are the main elements here. The turbine work output is equal to H1 minus H2. And of course, the turbine work will be positive. Some of you in the exam, maybe one or so, I know they understand that, but by mistake, they put it negative. It does not look nice if this will be minus 10 or something. This is not good. So this is a turbine here. H1 minus H2 will give us W turbine. So remember here that this is the equation for turbine, and this is a simplified equation. Simplified means that we neglected kinetic energy, which is there. We neglected potential energy, which is there. But because they are small with respect to delta H, therefore we can neglect them. For the condenser here, we write the energy equation. So we have Q out is equal to the change of enthalpy from 2 to 3. So Q is equal to H2 minus H3. It is Q out here. Okay, then W pump, it's H4 minus H3. Then boiler, the heat added here in the boiler is equal to H1 minus H4. So these are the analysis from thermodynamics 1 to each one of these components. No mistakes on those here. So with this analysis here, we know that we have to give the work for the pump here, and then we get the work from the turbine. This goes to the generator and goes to electrical engineers to produce the power or the electricity that we have at our home right now. Then this is here in the boiler. We add fuel and air here, and the heat from the combustion here goes to the evaporator, and therefore in the boiler here there is an increase in enthalpy from 4 to 1. Please stop me at any point if you have any question or anything is not clear. So now what we are looking for, what do you want from this cycle? We need two things, as I mentioned. This is what we call the performance parameter. Performance parameter is like GPA and like experience. This would be the performance of a student. So now we have the work. So this is W, the cycle. So this will be W turbine minus W pump. So we calculate this W turbine, H1 minus H2 from the previous slide, minus W pump, H4 minus H3. Then, so this is the work, the power is. This is what we are looking for. The second performance figure is the efficiency. We divide W cycle by Qn. This will give us the efficiency. So these are the two main parameters for this cycle, the two main performance figures. We need to increase the work. We need to improve the efficiency. So these are the two main. We have another one here, which is back work ratio, means that what is the ratio of W pump over W turbine. So in this cycle here, we give work and we get work. So now is this, as far as this is small with respect to that, then this is also very good. So these are the two main parameters, W and eta, and this is the third one. It's less important, but it's also important to compare W pump over W turbine. All right. So this is the Rankine cycle, and now I'm going to consider the analysis. So when we say here ideal, we're going to study ideal Rankine cycle. As I mentioned, Rankine cycle presents the simple power plant cycle. So you remember that this complicated figure we gave last time, this is the actual cycle like in Ghazlan, Quraya, and some of you already submitted animations for that. So the second thing here is that, so this is a simple cycle. Now we are considering now ideal cycle. Then later on we move from being an ideal, and we remove from being simple. So we change that to real cycle. So when I say ideal cycle, means that the friction pressure drops are neglected, and also there is no irreversibility. They are adiabatic. So we consider isentropic process in the turbine and in the compressor in the pump, and we neglect the pressure loss. All right, so now we have this is, let us present this here, what happens in this cycle. Okay, so I'm talking now, this is the TS diagram, and I have the four processes, so let us review this. So process 1 to 2, One is the isentropic expansion from the state 1 to state 2. So this at the inlet of the turbine. So now we have this is here. And then we have the next is 2 to 3, which is in the condenser. So this is condensing, changing from liquid plus vapor or fully vapor to liquid at state 3. Then we have 3 to 4 is pumping. So this is pumping liquid here. It is a liquid, so this is why we call it a pump. It's pumped from 3 to 4. And then the last step here is in the boiler. So in the boiler, it is heated from 4 to 1, and the cycle continues like that. So this is here. Of course, there's some possible variations that one may be superheated, so it will be 1 dash, and then 2 dash will be here. So this is normally the cycle here. In actual cycle, it goes like that: 3, 4, 1 prime, 2 prime, then 3 and 4. So this is a cycle in the simple power plant. Okay. Then for regarding the turbine, if compressor turbine boiler, so we have H1, H2, H3, and 4. For the case of the pump, when we go to the pump here, when we go to the pump, it is in the compressed liquid region. And you may not find this to get H4 here, you will not find it in the tables. And therefore, we should go here and say that W pump is equal to integral of VTP. So we get V3 multiplied by delta P, P4 minus P3. So this is the procedure to get W pump. I'm going to have example soon regarding this. If we apply here the energy equation integral of the TDS, then we can see here that I have two areas here. Let me go first to this area. What is this area here? This is the area under the diagram from 4 to 1. So this is the area here under 4 to 1. So this is the heat added is the area 4A1 dash, which is 2 to 6. So this is the area here. Let me just get this off. So the area here is the area under this diagram. This represents the heat transfer to the water. Then the second area here is this is QL. So it is, we can say that the efficiency is W net over QH, or 1 minus QL over QH. So this is here, and of course this area here, 1, 2, 3, 1, 2, 3, 4. This is the area that's the work done. So the area under this curve here, this is the heat added. The area under this curve, this is the heat rejection. And therefore, the area enclosed here represents the heat that has been transferred to Earth. So this is the network done by the cycle, okay, which is this one here. So this is the network. This is the area here. This is QL. Adding QL plus work, this will give me QH. And therefore, 1 minus QL over QH, the area, all of this area, will give me the efficiency, or it is W, which is equivalent to that, over W plus QL, which is actually QH. So QL, this is QL, the area here is QL. This area is the work. Work plus QL will give me QH, and therefore eta, which is equal to W over QH, which is all of this area. Okay, I'm going to take an example here. But this is just from another source, so we'll just change the points here. So this will be 1 to 2. This is inlet to the pump, 2 to 3 in the boiler, and then 3 to 4 in the turbine, 4 to 1 in the condenser. I just wanted to show you how do you calculate the properties, how do you solve a problem for a simple cycle. So the example shows here. Okay, what do we need from us? Okay, so the question here, calculate the work and calculate the efficiency. It's always like that. What is the work and what is the efficiency? Like the performance of the students here, what is the GPA and what is the experience you have? So now what I need here, the question will be like that. Calculate the net power, calculate the efficiency of the cycle. Okay. So now this is calculate the thermal efficiency of an ideal Rankine cycle. Ideal means that this is isentropic. This is isentropic, no pressure losses, so 2 is equal to 3. No pressure losses here, so 1 is equal to 4. Of course, it will give us here how many pieces of data. Now I want to fix state 1. So now state 1, I give the pressure, and I say that x is equal to 0. So in this case, I fix state 1. Then we give the pressure for 2, therefore I know the direction here, so I go from 1 to 2. Then he will give me, this is going constant pressure, and then we have to have a temperature here, so it gives you the maximum temperature. Then I stop at this point, then this is expansion to this pressure. So normally they give us pressure 1 and x1. The quality is 0 here. If it does not give me x, then I assume it is 0, because this is saturated liquid here. So it gives me P1 and x1. Then it gives me the pressure of 3 and T3. So we need 4 pieces of data. So it's giving us here the pressure of 3 is T3, and the pressure, the temperature is T3, and then it's giving us 10 kilopascal here. So we know the pressure here, I know the pressure here, and I know the temperature of T3. So these 3 pieces, I need 4 pieces, and therefore we'll assume here that x1 is equal to 0. But this is by default. If not given, then assume right away x1 equal to 0. Okay. So now we start solving this, and we have, this is the equation here for to get the pump. For the pump, we say delta H is equal to integral of VdP. This is valid for any ideal, any isentropic process. But here, integral of VdP, if V is constant, then I can take it out. And this happens only in the pump, not in the turbine. And therefore, in the pump, I say here that V1, V is constant, so I say H2 minus H1 is equal to V1 P2 minus P1. So now the solution here is that I will go to this here. I need to calculate the enthalpy at H1, enthalpy at H2, 3, and 4. So the first step is to calculate the enthalpy at 1, 2, 3, and 4. Then from 3 to 4, I can get W turbine. From 1 to 2, I can get W pump. From 2 to 3, I can get QH. From 4 to 1, I can get QL. And accordingly, I can get the efficiency and work. So now we'll go here and go to the table. I have P1. This is at the liquid. Is P1 is equal to 10 and saturated liquid. And then so I can go to the table and calculate H1 as equal to HF. This is simply. But I need also V1 because I'm going to use it here. So I go to the table and also read this one. It's always something like that, 0.001 something here. Okay, so this is all the same here. You can neglect these parts, but it is 1 over 1,000. Why 1 over 1,000? Remember that this is the specific volume of liquid water. It is 1 over the density, and the density is 1,000. Okay, let me just go and take attendance now so I do not forget. Okay, it's done. Okay, Shabab, now you still see the screen? Shabab?
Yes.
Yes.
Okay. So I'm continuing now. So we'll go calculate all the properties. So at state 1, which is we get P1 is 10 kilopascal and saturated liquid. Let me just go back here. So this is state 1. How do you define state 1? I know the pressure, and I go get at this pressure at this point I get HF. So this is the first point. Then I get W pump. W pump is equal to V1, which I got here, multiplied by delta P, which is P2 minus P1. Let me just go to the diagram again. So this is P2 is given, P1 is given, multiply here by specific volume here. So this will give you P1, P2 minus P1. You don't have to memorize anything, but you need to apply it. Everything will be in the formula sheet, the equations, but you need to apply this here. I just want you to remember this value. W pump is equal to 6 kilojoule per kilogram. Can you remember this? Can I have one student say yes, I remember this, so we can, next time he tells me what's the value. Any volunteer?
Okay.
What's your name?
Yazid.
Yazid. Okay, Yazid will remember here that W pump is 6 kilojoule per kilogram. Okay. Then, so now we calculated W pump. Now we say here that H2, how to get H2? I go back to this equation here and say that H2 is equal to H1 plus this value that we calculated here, plus W pump. So now I can calculate H2. You can see here that H2 is 197, H1 is 1981. So the difference here, this is a 6, that value 6 here, that this is Yazid reminds us later on. So you can see here that H2 is approximately equal to H1. It's not much difference here. Okay, then we go to the boiler. Go to the boiler. In the boiler, the equation is Q is equal to M dot H3 minus H2. Let me just go back to the diagram. So in the boiler here, I need to calculate H3, and we have already calculated H2. So the difference here, this would be QH. So now we go to the equation. So we say here Q is equal to H3 minus H2. So now I need to calculate H3 and H2. How? We go to the table. P3 is given, T3 is given, and therefore we get H3 and S3. Can I ask someone why are we getting S3? Any volunteer to answer this? Why do we need S3? No answer, Shabab.
To fix
Because
the
it's
space
isentropic process.
Okay, very good. Because this is an isentropic process in the turbine, so I need to get to use it here. This is the way I define this state. I go vertically here, so state 4 will be S3, the same S4 is equal to S3 plus the pressure here, so this will give us state 4. Very good, thank you. So now we go here and calculate Qn is equal to H3 minus H2. Well, don't forget about M dot now. Don't, even if you are given M dot, do not apply M dot. Only at the end you can apply that. So we're working now per kilogram. So calculate H3 minus H2, and this is the value you get here. Then we'll go to the turbine now, and the turbine here is H3 minus H4. So now how to get S4? This is the idea here, is we say that S3 is equal to S4, but then we say, so this is the equation here, we get S4, then I have a state here. I have the pressure is given 10 kilopascal, and S is equal to this value. So now I have to check, is it in saturation region? It is superheated. So if S4, of course it is cannot be in compressed liquid, so it is either in saturation region or it is in superheated region. So with this here, you are expert in that, so you can define which value. So it comes here to be in saturation region. So I go and calculate H4 from the table and get that. Then we calculate the turbine work, H3 minus H4, and then we get here, this is W turbine. So now I ask Yazid here. So now the network is equal to a W turbine minus W pump. So can anyone else remember this value other than Yazid?
Yes, doctor.
Name?
Hassan Sirati.
Okay, Hassan. So remember W turbine here is equal to this value, 1000. Now we go to calculate W net. Here I need Hassan and Yazid. So you see here that W pump is 6 and W turbine is 1000. I'm sure that if you have 1038 real and if you lose 6 real, you are not going to spend all night looking for this 6 real. So just leave, look around. If you don't find it, then leave. So it means that here, this is the small with relative to that. So in this case, for the thermal power plants or for the Rankine cycle, normally W pump is small for that. We have to calculate it here, but remember here, if you see that this is very close to that. If this is not very close, it's better for me to neglect that, to put it 0, other than having 600 or whatever here. So remember that this value W turbine is approximately equal to W net. So because this is normally small, this is in the thermal power plants. And I want Yazid and Hassan to remember this here, that W pump is neglected with respect to W turbine. Remember this for 3 weeks from now, huh? Because I'm going to another chapter after 3 weeks, and we will compare for gas turbine for next chapter, chapter 9, with this chapter here. So remember Yazid here and Hassan that W pump is very small in that with respect to W turbine in the case of Rankine cycle. And I will ask you this question again 3 weeks from now. Okay, then, so this is the important part here. This is the first performance figure, that there is a W net. And all of what we are going to do in this chapter is to try to improve this value as much as we can. Similar to improving the power of the car. You get 8 cylinder, 6 cylinder, you have injection, you have supercharging, turbocharging. So all of these here are made to improve the power. Also, we'll have some things here to improve the power. Okay, then we have the thermal efficiency. This is the second important part. You divide W net by Qn, and this gives you here 36%. This is a typical value. If we go to the real power plant, it will be around 45%, something like that. Okay, so these are the two main parameters that we are looking for here. And of course, the third parameter is W pump over W turbine, which we call it work back ratio, and this is neglected in this case here. Okay, so this is what I wanted to have as an example here. So now this example explains how do you solve the rankine cycle. Okay, so I want you to go home, you're already at home, to work after hours today and solve this example by yourself. Please go to the problem, solve it, and then get down. This case or any example of the book, and any example in anywhere, just have an example and solve it yourself. Make sure that you get the correct data. Of course, the procedure in thermodynamics too always will be like that. So we'll get enthalpies, where's the first step. Then we calculate W net, W turbine, W pump, and so on, QH, and then we calculate. So the procedure is systematic. But the values are very important here. Why? Because I need to this. If you get me this negative, means that you buy a power plant and then you do not produce electricity. Other than that, you need an electricity to. This is just amazing here. So if you find that all of us do mistakes, so we can get W net say negative here by mistake. But then you cannot leave it like that. You have to comment it. Just say it is impossible. So I understand that you know that. You do not agree to this value. All of us do mistakes. W can become negative because it's mathematics here. But you cannot leave it like that and leave the exam. You have to say here that this is negative. It is impossible to have that. The efficiency here cannot be negative, of course. Cannot be 100%. Cannot be negative 90%. So also, can it be more than 1? So all of us do mistakes. It can happen here, but I cannot leave it like that. So say impossible. If you have time, then of course you have to go back and calculate. The second issue I wanted to say here, so the numbers are very important to me. Okay, it gets me very angry when I see W is negative or efficiency is more than 1 or negative or something like that. Just comment here. That's say impossible. Then the second point I want to ask you, when you solve, do not put the mass flow rate. Solve per kilogram. Then at the end here I ask you what's the power, so you multiply by m dot to get it in megawatt or in kilowatt. Okay, so this is the issue. Do not introduce m dot in each stage. This is tedious, but I want you to solve per kilogram. Then after that, you multiply by the mass flow rate. Okay, any questions, Shabab, in this example? Okay, how many of you will not be able to solve an example like this from the textbook or anything? Anyone does not have the potential? Shabab, I don't see any excuse. Just takes about 5 minutes to pick an example in the book or any book you have or in the internet, whatever. Get an example, solve it, and just satisfy the values, calculate the values here, and make sure that you get the symbols. All right. So this is the first step here. We have the simple ideal cycle, and we had an example in it, so you should be expert in calculating that. So this is the first step we have in this chapter here, is to see how do we calculate what is the simple cycle, ideal simple cycle, and then how do we calculate the property. Now the second thing here is that we will start now modifying this cycle. Modifying this cycle, I mentioned two things. I need to increase the power and I need to increase the efficiency. Okay, so now let us see the cycle here. It is 1, 2, 3, 4. This is the net power. Okay, I want someone here to tell me how can I increase this power. This is the area here that presents the power. Okay, so we have choices here. One of the choices here is to reduce this pressure. If instead of 2, I go to this pressure here, means that I have this area means that I'm adding this area here. Okay, let's look at this again. This is the power, net power out. 1, 2, 3, 4. All right, so this is the power, net power out. And we want to improve the power here and also the efficiency. How can I improve the power? If I have three things, three possible ways here, I'm going to study them. I'm going to study first, changing the condenser pressure. Change the condenser pressure. If I reduce this here to be this one, did I increase the power or not? يا شباب.
Yes.
Okay,
Yes.
Yes.
increase it by what?
Yes.
By this area here. So instead of having 1, 2, 3, 4, I have 1, 2 prime, 3 prime, 4 prime, and so on. So this is here. One way of achieving this is to reduce the condenser pressure. All right, let us see the advantage. Yes, the advantage here is that you have improved the power. How about the efficiency? Did I improve the efficiency or not? Remember, the power increased, but the heat added also slightly increased. But let us go to something else here, that let us check Carnot cycle. If this is a Carnot cycle, and if you reduce the pressure in Carnot cycle, I think I had something here regarding this Carnot cycle, huh? Okay, no, it's not here. Right. Okay, Carnot cycle is a box like that, right? It is 1 minus TL over TH. So now if I reduce TL, means that the efficiency will improve. Remember that Carnot cycle 1 minus TL over TH. If I reduce TL, means that this is the efficiency will be improved, will increase. And we will not, this is of course not Carnot cycle, but we take it as a guidance here. So as far as I can reduce this temperature or increase this temperature, then definitely the efficiency will be improved. So now I can say here that as a result of that, we have improved the power and the efficiency is improved. I want to discuss something else with you here. Okay, this value here, x here, is very important to us. In practice, we have x here has to be close to 1. Why? Because you know this is at the exit of the turbine. And the turbine, you have seen that the turbine have blades, and these are droplets here. Droplets, when you have a droplet on the turbine blade, it will cause erosion. You know what's erosion or not? Okay, let me ask you one
Yes.
thing here. Have you seen any cars? Somebody is covering the head of the car, and I have seen some people in the desert or so بيغطي الترانك بتاع السيارة. Why is that? Have you seen this first or not? Anybody have seen that? يا شباب. Anybody there?
We haven't seen that.
Yes.
يعني في سيارة، أنا أشوف سيارات كده بيبقى مغطي الترانك بتاعها بسامسونج، يعني مغطيها بكفر كده أو حاجة وهو ماشي في الصحراء. Anyone knows why?
To protect it from erosion.
Very good.
Yeah,
What's erosion؟ اللي هو الرمل اللي بيطلع عليها زي ما تقول بيكحت فيها كده. It erodes the cover bed. So this is here, when it goes to sand, then sand erodes the paint, and this is what we call erosion. This happens the same here. When you have a droplet of water here in the turbine blade, it cause erosion to the turbine blade. بيحصل لها تآكل. Not تآكل is corrosion, but it is what we call erosion. Corrosion is with chemical reaction. Erosion, no chemical reaction. It is just eroding the plate, the painting. So this is here, is that we want to keep this here as close as 1 here. So now we have an advantage that will improve the efficiency and the power. We have a disadvantage that x here decreased or increased. When I go from 2 to 2 prime, the quality x increased or decreased?
increase.
Decrease.
Decrease, because if you go this direction, it goes to 1. If I go up, it goes to 1. Therefore, if you go down, it goes less. So now it is decreased. So this is a disadvantage here. So I have an advantage improving the power and efficiency. The disadvantage that x is decreased. Type. So now we have advantage, we have disadvantage. Now I want to have, is there any limitation? Can I reduce this to any pressure or not? اللي هيجاوب السؤال ده له بونص كويس. Is there any limit for this or not? Can I still keep reducing? Why? And if reducing this improves the efficiency, why don't I keep decreasing this here? Anyone wants to take a bonus?
Below that to
Uh,
go will not sufficient for the pump.
The density, you mean?
No, not the density. If we need to increase it to the turbine pressure again.
No. Okay. Type. Okay. Another answer. Anyone else?
we will need more work in the pump.
All right. This is very good. So this
Yeah.
is a part of that here, but this is a disadvantage, not a limitation. Of course, here you need a pump. Why do you need that?
عشان
But
يرفع
remember,
ضغط
remember who said that? Who said that? We need more
Yes,
power, more
it's
power.
me, Bakr Joe.
Who?
Yes, we will need more power in the pump to return it back to the
All right. Type. Let me go back to Yazid.
higher.
Do you remember what Yazid? What is the power Yazid? Remember what Yazid and Hassan mentioned? What the W pump is negligible, right?
Negligible.
Yes.
So if it is 6, are
Yes.
you going to make it 5? Yeah. So what? This is so it is. This is yes. It will increase the power, but we are talking about negligible part anyway. As a matter of engineering, after when you be an engineer and you work this cycle analysis, you neglect all of that here. But the limit here is look at that. How are we going to do the cooling here? How do we cool this here? We cool it by water from the atmosphere, the ocean or the river or something like that. And therefore, we cannot reduce this below the ambient temperature. So we can reduce this here, but when we reach 25 degrees here, we cannot because I am cooling this by ambient water, liquid water, at ambient condition. And therefore, the limitation here, if when you go to this pressure here at 10 kilopascal, you find it 40 degrees centigrade. I cannot reduce more below than ambient temperature. So this is the limitation here. All right. So now we'll go now to the next. So now we have seen here how to improve the power and efficiency and we discuss this here by reducing the condenser pressure. Now let us see something else. Okay, so it is written here why we have this because we cannot reach the atmospheric condition. All right. So you see this is the limit here that has to be above here the ambient temperature. All right. Let us go to another thing here. Is that another issue here is to raise the pressure here, to raise this pressure up. Okay, so in this case, let me go back. So in case here, I want to increase the pressure. So now we have, this is the original one. Let us go to the original one again. Okay, let me go here. I think this is the condenser pressure. The second one is to increase the boiler pressure. So now the other choice here, now instead of increasing this, I can increase this. Remember here what I'm doing now, I'm seeing the possible ways of improving the power. And of course, we'll find the advantage, disadvantage, and limitation. And from this, we are going to modify the cycle and avoid the disadvantage and so on. So this is just an analysis here to see the ways of improvement. So the other way here is to improve the power is to go with this up here. If I go with this up here, then I am trying to improve the power by adding something here. But of course, I'm going to lose part here. So I can say here that will this improve the efficiency or not? When I move this from this point to this point.
Yes. It improves.
Why?
No.
Because TH will increase. So 1 minus TL over TH will be more. Remember, I'm not calculating the efficiency of the cycle, but I'm calculating the efficiency of a Carnot, and this is a guide for us. For us, follow the cycle for Otto cycle. Do not use the equation, but as far as you increase TH, the efficiency will improve. As far as you reduce this, the efficiency will decrease. So now this is here is the efficiency of the efficiency will be improved, and the power we are not sure because we added this part, but we lost this part here. Now what happened to so these are advantages, the efficiency improvement. Work, I'm not sure about it. How about the X here? Is it improved or Decrease. So it is a decrease here. So this is a disadvantage. Okay. Is there a limitation for this? Of course, there's a limitation because these are tubes in the boiler, and the material engineer tells us here that you will have more stresses, so you cannot increase this more than a certain value. So these are the advantage, disadvantage, and limitation. Okay. Another way here, so this is the thing here, is that we move the pressure from this to this here. And this is what we talked about now. So this is the second option to have. The third option is, let me go to the third option. You see here is discussing here that X has decreased, and this is a disadvantage here. Okay. So now let us go to the third one here. The third one is increasing the superheat. So now we have here, this is the original cycle here, 1, 2, 3, 4. How about superheating this? Instead of 1, we have it 1 prime. What happened to the power? Increased or not?
Yes.
Increased by this
Increase, yes.
amount. Okay. How about the efficiency? Remember that we have increased the power, but we have increased the QH as well. So W over
Yes.
W has increased, QH has increased, and therefore the efficiency has W increased over QH, which is increased. But anyone, I can give a bonus here. Anyone will tell us the efficiency improved or not? Say your name, please.
Not Faisal Atabi.
Name and answer.
Faisal Atabi, the efficiency is not improved here.
It's not
work,
increased.
yes.
Okay, Professor. Anyone else? Type, what
It's
happened?
increasing.
It's increasing. Did it
Yes.
increase or who is that saying yes?
Hassan Sehati.
Okay, Hassan, if you give me the reason, I give you a bonus. What's the reason? Okay, remember you always forget. Did TH increase or decrease? What happens to TH?
Please.
TH increase.
Take the average here. TH from A to 1 or from A to 1 prime. So TH here
From
was
A.
A to 1. Now it is A to 1 prime. So the average has increased, right?
Yes.
So it means that TH has increased, means that the efficiency is improved. So now we have efficiency is improved, the power is improved. How about the quality here?
Improved.
Improved. So all this advantage here.
Improved also.
What is the limitation? Is there any limitation I can go with this all the way or not? The limitation will tell us, the material engineer will tell me here, stop at this point. You cannot have a temperature here because the turbine is blades and working. So it tells me here you cannot go more than 500, 600 degrees centigrade. So the material engineer will tell me to stop here. So now we have seen 3 ways of improving the performance. It is reducing the pressure of the condenser, increasing the boiler temperature, pressure, and having superheat here increase the temperature at this point. But everyone has an advantage, disadvantage, and limitation. So our way now is we need to develop a cycle that will take the advantages and avoid the disadvantage and limitation. And this will be our next step here is to, so you can see here, this is explaining how X2 is increased and how the power is increased. Therefore, next time, we are going to take a new cycle, which is ideal reheat cycle, and this will take the advantage and disadvantage. So next time, we are going to study ideal reheat cycle. I will stop at this point, and then I answer if you have any question in this here. If not, then we can answer your concerns about the grades and so on. Any questions, the class?
Doctor,
Yes.
the second improvement, this is what we call heat regeneration, right?
The second, this is okay. No, the heat regeneration will be one of the modifications here. One of them will take ideal heat cycle and regenerative cycle. Regenerative cycle is that it will be related to, okay, it is just here I wanted to say here that, why is the improvement here? In this part, it is that we have raised the temperature at the boiler inlet, and therefore we have less irreversibility here, and this is the reason. So it is, yes, you are in a point, yes, we have improved. This is like regeneration, or what we say here, reduce the temperature difference or reduce the irreversibility in the boiler. I will talk about this next time, inshallah. But you are right, this is towards regeneration. Any other questions? Okay, I had a question regarding the grades for the quiz. You're saying that it is too much for a quiz to have 10. Okay, I mentioned 10 because this will be the maximum. What I'm planning to have is that every chapter I will have a quiz. So if I make it 5 to 10, approximately, if I say it, let us say maximum is 10 here, so 10 by 8, then I have 80. I'm not sure about what happens next time, after 7 weeks, but for this 7 weeks, we are not going to have a measure. The measure is already distributed to quizzes. So we have 20 points as quizzes, and we have about other 20 points as quizzes, so I need 40 points. So this is why I'm taking every chapter, I'll take a quiz. And then I may drop the worst quiz later on. I'm saying I may, if I have many quizzes. Okay, and then, but it will be maximum 10, it will be minimum 5. All the quizzes will be the same, but it may be 8, it may be 10 or something like that, depending on what happens. I don't know about the end of the next part of the term, the next 8 weeks. They did not decide yet, is it online or face-to-face. So if it is online, also we are going to reduce the final exam. The second measure will be also quizzes. So this is why I have to depend on quiz. But I will do my best to drop the worst quiz. If I have 6 or 7 quizzes on each chapter, then I promise to drop the worst quiz. But you have to be prepared that the quiz will be maximum 10 points, will be minimum 5 points.
دكتور
Yes, please go ahead.
بس بالنسبة حق هذا الكويز يا ريت أعطيتنا خبر قبل إنه بيكون عليه هذا الوزن حق نستعد لأفضل وأفضل، يعني إحنا أكيد نكون مستعدين
طب خلي
الكويز.
بالك، انا والله ذكرت الكلام ده وقلت it's 5 to 10. One asked me in the class, I told him between 5 and 10.
تمام.
I remember that. One in the class asked me what is the value for the quiz. I told him 5 to 10. And I'm still with that. I'm saying 10 is the maximum.
تمام
Okay?
تمام.
10 is the بس والله مين معايا؟
علي الحاجي.
مين؟ علي. Okay, علي. والله أنا remember this. Anyone remembers mention from 5 to 10. So I'm not increasing more than 10, and it will not be 10. It may be 8 or so. But I have to say the limit here, so do not complain after that. The maximum is 10, but it will be lower than that, inshallah. And I promise you, inshallah, I will drop the worst quiz. All right? Inshallah, Alam. Any other concerns? I'm giving another class for my fellow Dr. Saeed at 10, but still you can have 5 minutes questions. Any other concerns?
طيب دكتور, what if you increase the amount of quizzes we get so you can distribute it easily?
والله ما أنا قلت لك أنا I have after each chapter I have one, so I have 7 chapters, so this will be seven quizzes. You need more than that? I don't want to have quizzes outside the class. This is one issue. I don't want to disturb you at night by quizzes. I don't like this issue. It is disturbing the student. The second is I'm giving this in class. And of course, also I have material to give, so I cannot give more than 7 quizzes or 8 quizzes. So 7 quizzes, I think that will be quite enough. Yeah.
I mean like 2 quizzes for each chapter, for example. Or is that not possible?
والله يبقى too much يا شباب يعني. Let me think about it, okay? I'll try to think about it. So you want small quizzes, 2 small quizzes rather than 1 big quiz. Like the previous one, I can make 2 problems, 1 at each time. Yeah. I'll think about that, inshallah.
For example, maybe you can make the first quiz as conceptual for the chapter and the second quiz as numerical for the chapter.
I promise I will think about that. Yeah. خلاص, okay.
Thank you very much.
You are welcome.
دكتور حددت فسور بيكون.
I'm sorry?
حددت متى لو فسور بيكون ولا لسه؟
لا انتوا تحددوا لي الوقت لان انا ما يعني I need some time to be acceptable to it can be at night no problem with me. So انت يا حسن مرر وقت كده كل واحد يقول الوقت بتاعه وشوفوا good time for you.
Thank you.
Put on WhatsApp one time or two time slots. One, for example, Monday and Wednesday, or any 2 days that you don't have labs in them. And then I do not have to have all the students. Maybe put two slots. But if one of them suitable to one student, some students, the others are suitable for other students. That's fine. Okay, but at least one of them should be suitable for the two will be. I mean, all the students can attend the two of them. So try to make this for me. I can put a date. We can assign a date now. How about, for example, 6 p.m. on Sunday in any day, 7 p.m. Any time for me is fine with me. But I want it to be away of your labs.
We can do Google survey and we'll see the most suitable.
Please do that. I mean, make it on WhatsApp and give me 2 slots or 3 slots. I don't mind. Okay, Shabab. But the slots, those slots will be 1 hour, for example. I'm not going to sit in 1 hour. I'll make it 15 minutes. So you can attend 15 minutes, but if students are there, I will continue with them. All right? But if no students come in within the 15 minutes, then I'll close. But if you are there, I can continue 1 hour, 2 hours, no problem with me. But students have to be serious and join at this time. Yeah. Because I used to have in the office, I stay all the office there, and maybe 1 or 2 students come. So I'll make it 15 minutes, but it is extendable. If some students are there, I can continue with them. Okay. طيب خلاص Hassan, you will do the job, please.
Yes, doctor, inshallah.
Thank you much, Hassan. Jazakallah khair. And any questions you want, ask on the WhatsApp. Hassan will send the concerns to me in email. And then I will answer him and then he can give. So just to control that nobody gives anything and only Hassan will give you the things that I agreed with him about that. So just, okay, thank you much. Any other questions? Questions, شباب؟ طب shall I close؟
يعطيك العافية يا دكتور.
الله خير، جزاكم الله خير، شكرا جزيلا، السلام عليكم.